Okay, welcome back to Calculus. We're going to wrap up section 8.3 with just a real quick video lecture on how to handle the centroid problem when we're looking at a region between two curves. So I've got two curves over the region, neither one of which is the x-axis. I want to be able to find the centroid. Also in this lecture, I want to include something called the Theorem of Pappus, which is a way to compute volumes of solids of revolution without using disks or shells, but you do need to know the coordinates of the centroid of the region you're revolving. It's a very cool theorem. Okay, so let's get going. I'm going to make this super quick. You can almost just sort of say, like, here are the formulas if you want, but just as a quick derivation, if you give me two functions, f and g, on an interval from a to b, they don't cross. One is bigger than the other. In my notation, f is bigger than or equal to g. I want to find the centroid. So I'm going to make a local estimate. So if I look at this rectangle, it's an interval around some number x I've picked. Well, the centroid of that rectangle is its center. I'm choosing x to be in the middle, so that's the x coordinate of the centroid of just the rectangle. The y coordinate is, well, it's the average of f of x and g of x, because g of x is the y coordinate at the bottom of this rectangle, f of x is the y coordinate at the top, and their average would be the y coordinate right in the middle. Okay, so that's the centroid of my rectangle. All right, so then how do we write down these formulas? What's the mass? If you take your constant mass density rho, and you multiply it by the area of that rectangle, the area of that rectangle is certainly f of x minus g of x times its width, dx. I've already taken the limit. Then that should give you the mass, yeah? Mass times area, mass density times area is mass. So that's how you compute the mass of the thing. You just rho times the area. Area is top curve minus bottom curve, like back in chapter 6. Okay, we also said that when you want to compute, say, the moment about the y-axis, you take the x-coordinate of the centroid. Okay, so I'm just thinking about this rectangle locally, but I've just written the integral already. And then I need to multiply the x-coordinate of the centroid by what? I need to multiply the x-coordinate of the centroid by the mass. Well, we've already said that the mass of that rectangle is the mass density times its area. Its area is its height times its width. So the moment about the y-axis is just rho times x times f of x minus g of x, top curve minus bottom curve again. Okay, this last one, maybe I want to put in a little bit of an explanation. So we've already said that the y-coordinate of the centroid is 1/2 f of x plus g of x. So if I was trying to estimate m sub x, I would say, okay, well, let's take that y-coordinate of the centroid, 1/2 the quantity f of x plus g of x, and multiply it by the mass of the rectangle. Well, the mass of the rectangle, again, is rho times f of x minus g of x, that's the height of the rectangle, times your dx, that's its thickness. And if you assemble these pieces, I think you can see that the 1/2 times the rho is in my integral. And then just check this out. If you multiply f plus g by f minus g, that's a difference of squares. You get f squared minus g squared times your dx. So that's how you calculate the moment about the x-axis. It's 1/2 rho top curve squared minus bottom curve squared. All right. Just like before, the centroid's coordinates, x bar is the moment about the y-axis over the mass, y bar is the moment about the x-axis over the mass. So you can basically stop there. These three new formulas are how you treat in the case that the region is bounded by more than one, but it's not bounded by one of the coordinate axes. It's not bounded by the x-axis. You have to put in the g of x in the formula there. Check these things out. If g of x is equal to 0, if you zero out g of x, then it certainly just recovers the formulas from the previous lectures where it was always bounded by the x-axis below. So just a quick computation. I've kind of written this out, so I'm just going to narrate it rather than writing all the details. But I would encourage you to kind of stop and see if you can do it without me. But the example that I picked, I want to take the top curve to be the exponential and the bottom curve to be linear. G of x is x. Doing this over the interval from 0 to 1, so you can see my region R is over here. And I want to find its centroid. I want to find x bar and y bar. So I got to compute those three quantities. Mass, moment about the y-axis, moment about the x-axis. Okay, so the mass is the density times the integral of top curve minus bottom curve. Let me just sort of, you can stop the video. I'm not going to actually talk very slowly here at all, but I just found an antiderivative for e to the x minus x. I'm carefully evaluating it at 1, subtracting its value at 0, and that's my answer. I'm not using units in here, but if, say, a rho was in, if you wanted to use some units, if we put rho in, say, grams per square centimeter, right, then the area would be measured in square centimeters. And so this mass would be in grams, for example, all right? So whatever your unit system is. How about m sub y? M sub y, the calculation is, well, from the formula above. It's rho integral of x times f of x minus g of x. Okay, I distributed, and I'm going to treat those two integrals separately. First integral is a parts integral. Integration by parts, x times e to the x. Its antiderivative is x times e to the x minus e to the x. Second integral is just a power rule. Okay, and then I just plugged in 1 into all three of those, x times e to the x minus e to the x minus a third of x, then plugged in 0. Evaluate it all out, you get 2/3. 2/3 rho, excuse me. Okay, 2/3 rho. Nice. How about the m sub x? Okay, formula says it's 1/2 top curve squared minus bottom curve squared. E to the x squared is e to the 2x, x squared is x squared. Antiderivatives, little substitution, 1/2 e to the 2x minus 1/3 x cubed, evaluating. Plug in 1, plug in 0. I hope you're stopping the video and checking all this stuff. The way I did my math, I ended up getting 1/2 that quantity, and I pushed the half through there. I'm going to write it like that. Rho is rho times the quantity 1/4 e squared minus 5/12. That's my mx. And then you assemble it. You assemble it into your centroids. Okay, so x coordinate of the centroid is moment about the y-axis over m. We computed it above. It was 2 rho over 3. Mass was rho times that quantity. Of course, the rho's cancel. The x coordinate of the centroid is independent of the density. So I get that rational, or sorry, this fractional expression here. As a decimal, it's about 0.55. Same thing for y bar, mx over m, cancel the rows. There it is as an exact value. As a decimal, it's approximately 1.17. So I'm reporting my answers to the nearest 100th. And this picture is just to kind of show you to scale. You can look at the axes here. I've got my x bar and my y bar written approximately, and it looks reasonable. It looks reasonable. If you ever draw one of these pictures to scale, be careful here. You know, this is not in a 1-to-1 scale. Look, 1 unit on the x-axis looks like it's even longer than almost 3 units on the y-axis. So this picture has been compressed. Often pictures with exponential functions will compress the y-axis because otherwise the picture has to get too big. But it doesn't look completely unreasonable that that would be the balance point. Yeah, 0.55 comma 1.17. Nice. Okay, so you can try some of those. I'm going to end this thing with this theorem of Pappus. It's kind of a cool theorem. It's saying that if you take some region in the plane, R, and then you take a line that doesn't pass through it, some line L, R is entirely on one side of it, and then you want to rotate R around L to form some solid. It would be some kind of wonky donut. Then this theorem is saying if you take the centroid, x bar, y bar, and you calculate its distance to L, so you find the distance between the centroid and the line L, that distance is called d in the statement of the theorem, so I'm going to do it the same way. Then the volume of that thing is calculated by the distance traveled by the centroid. Well, the centroid is traveling around a circle of radius d, so its distance is 2 pi d, and then you multiply that by the area of R. Okay, so you take the area of the region that you're rotating, you multiply it by the distance that the centroid travels, and Pappus's theorem says that that will give you the volume. Very interesting. I'm not going to give a complete proof of this theorem, but I do want to kind of give you some idea of why it's true, at least in the case that the region R is something like what we've done before with shells. So suppose that R is some region between A and B under the graph of f of x, and I want to rotate this thing, say, around the y-axis. Special case, but still. Okay, well, the shell formula says that the volume would be 2 pi times the integral from a to b of x f of x dx, right? 2 pi times x f of x dx. But that integral x f of x dx, that's exactly the moment about the y-axis. So that's 2 pi times, I'm just going to write it in here, moment about the y-axis. While you're saying it's missing the density, suppose that my density is equal to 1, just for convenience. I'm just trying to compute a volume here. I don't need to say anything about the actual mass. So suppose that I've sort of recalibrated and set the density equal to 1 unit of mass per square unit of area. Then the integral of x f of x dx is precisely the moment about the y-axis, right? But the moment about the y-axis, let's recall, if we wanted to calculate x bar is the moment about the y-axis divided by the mass. Yeah. So if I solve that for my, x bar times the mass is my. We've said this before, so I can write in here, replacing my, I'm going to replace it with x bar times the mass. But if the density is equal to 1, then the mass is the area, right? So 2 pi x bar times the area of our region. So that's what Pappus's theorem says, because here, if my centroid was x bar, y bar, indicating it there, then its distance to the axis of rotation in this special case is the x-coordinate. So this looks like 2 pi times the distance to the axis of rotation times the area. And Pappus's theorem is supposed to give the volume, and it does. Okay, so that's not a general proof of it, but it does give you kind of a special case. Nice. So let's just kind of illustrate really quickly. Here's our region that we looked at above. I've put this in a 3D picture, so if it's easier for you to see, if I drew, say, this arrow here, that's my x-axis. Oops. My x-axis moved on me. I don't want to edit this video again, so I'm just going to slop around with you guys a little bit here. And then I've got my y-axis. Maybe I won't try to be so fancy this time. I want an arrowhead on it though. There you go. There's my y-axis. All right. And then I've tried to show you in the depth of the picture here, the centroid, its location we marked was 0.55, 1.17 to some decimal approximations. So this is the path that centroid is going to travel if I'm rotating this region, say, around the x-axis. And so what is the distance that the centroid is going to travel? Well, the distance it's going to travel is a circle of radius y bar. Yeah, y bar is the circle's radius. So Pappus's theorem says I should take 2 pi times y bar times the area of that region. And here, just to kind of make the algebra a bit simpler, y bar is mx over m. Yeah, and if I set the radius equal to 1, then I don't have to worry about where those rows are. So the area of the region would be 1. And I can see that the the m's cancel, the masses cancel. So it's just 2 pi times mx, and we computed mx above. It's equal to that number. So that's faster, I think, than disks or shells disks if you can do this integral dx. Washers for this one. All right, so that's the theorem of Pappus. That's what I tell you about centroids. Thanks for listening.